Now it's a good time to overview VMware Secrets Manager's building blocks. As always, if you find value in what you learned today, please give us a star on GitHub at github.com/VMwareTanzu/Secrets Your support helps others discover this incredible technology. VMware Secrets Manager, or VSecM for short, uses Spire as its identity control plane. Spire is a runtime implementation for the SPIFFE protocol. You can learn more about SPIFFE and Spire by following this link. At a high level, we use Spire to distribute short-lived X509 digital certificates to workloads. This way, we can ensure that when a workload wants to communicate with a VSecM component, we can establish its identity and establish secure communication. Or to look at the other side of the coin, when a VSecM component delivers a message to a workload, the workload can check the X509 digital certificate of it and make sure that it's coming from a VSecM component and not an imposter. So essentially, using Spire, we establish mutual transport layer security, or MTLS, between workloads and VSecM using short-lived X509 digital certs. And those certs have a specific name in Spire terminology. They are called SVIDs, or SPIFFE Verifiable Identity Documents. Let's see this with an example. Assume a workload wants to fetch its secrets. Here's what will happen at a high level. VSecM Safe, which is our secrets store, will ask Spire for its identity. Spire will verify that VSecM Safe is what it claims to be, and it's not some random component that is pretending to be VSecM Safe. This process is called attestation. When Spire attests that VSecM Safe is indeed authentic and irrefutably and cryptographically verifies its identity, then it will provide VSecM Safe an X509 digital cert, which is the SVID. The same thing happens for the workload. The workload asks Spire, "Who am I?" And Spire will send a different X509 digital certificate to the workload once it cryptographically verifies its identity. If either of these components is an imposter, then Spire will fail to attest the component's authenticity and will not dispatch the certificate. When both Safe and the workload have certificates, they can establish an MTLS connection to exchange secrets securely. A side benefit of this approach is that since the workload's identity is part of its certificate, VSecM Safe will know which workload it is and dispatch only the secrets registered for this workload, and nobody else. In other words, a workload can only see the secrets registered for it. It cannot see any other workload's secret. This gives granularity, an additional level of security, and a protected blast radius in the unlikely event of a workload being compromised. If a hacker hacks into a workload, it will only see the subset of the secrets that belong to it. Any other secret will be unreachable. Another similar key exchange happens between VSecM components too. For example, VSecM Sentinel fetches its own X509 cert after being attested, so that we can make sure that certain VSecM Safe APIs can only be called from VSecM Sentinel. As an example, you can only register secrets to workloads through VSecM Sentinel. Also, this enables us to design the architecture such that a workload can read its secret, but it cannot update it or register a new secret. When it attempts those APIs, VSecM Safe will reject the request because the workload's identity does not match Sentinel's identity. Or, in other words, the workload is not Sentinel, so it is not authorized to use those Sentinel-specific VSecM Safe APIs. While discussing SPIFFE and Spire, we briefly introduced VSecM components such as Safe and Sentinel. Let's see them in a high-level diagram to clarify our understanding. In this diagram, Spire acts as an identity manager that distributes the SVIDs, the X509 digital certificates that all these components use to identify themselves. Those certs establish secure mutual transport layer security, or MTLS connections. VSecM Safe is our secure secret store. You can think of VSecM Sentinel as the bastion host, where you connect and register secrets for workloads to VSecM Safe. The demo workload uses VSecM Safe APIs to fetch secrets. As we'll see in the following sections, there are several ways for a workload to fetch a secret. You can use the VSecM Developer SDK when possible. This is our recommended approach. Or you can use the VSecM Sidecar to mount secrets to an in-memory volume dynamically. Or you can even interpolate the VSecM secret to a Kubernetes secret object and let the workload consume it by binding the secret as a volume or an environment variable. All of these approaches have their pros and cons, and they show the flexibility VSecM provides when it comes to how you want to consume secrets. I won't go into too much detail, but I'll just put this diagram here for reference. VSecM Safe has a bootstrapping workflow that stores its encryption master keys to a well-guarded Kubernetes secret. This way, if VSecM Safe crashes or gets evicted, it can restore its secrets from an encrypted backup store. We also have plans to use a cloud KMS or an HSM for the backing store so that we won't have to rely on Kubernetes secrets even when we know that the secret is well guarded, secured by tight RBAC, and can only be used by VSecM Safe. Next up, we'll talk about cluster SPIFFE IDs. Until then, keep your secrets secret.